to this session where we will try to explain to the audience why the seasonal forecast for climate services need to be tailored to the user needs and which were the challenges tackled by the SECLI firm project. So the content of this session is extracted mainly from the works performed under the work package 2 of the project. And the goal was to feed the most skillful seasonal forecast to a set of case studies, which will be presented in tomorrow's session, and to add value to the decision-making processes involved. The work performed can be divided in two main blocks. And the first one is the development of a multimodal seasonal prediction dataset from as many independent sources as we can. And the second was the development of a set of user-driven techniques with the aim of maximizing the prediction performance, its reliability, and the usefulness of the seasonal forecast. The work package was divided in 6 tasks. The first one covers the first action I mentioned before, so the development of a multimodal seasonal prediction dataset, while the tasks 2 to 5 are oriented to the development of seasonal forecasting techniques. The task 6 complements the previous ones, putting the project developments in the context of the progress made in other projects, bringing new ideas, disseminating the results, and helping to the overall improvement of the seasonal forecast systems. In the time we have today, the Work Package 2 team will explain you different techniques of seasonal forecasting, their particular challenges and limitations, and how they were specifically tailored to provide the needed information to the user. The session is divided in 2 blocks. And in the first one, we have 2 speakers. First one is Volmer Krieken, who will introduce us the added value of statistical seasonal forecasts, while Marcelo Perita has a presentation entitled Determination of Seasonal Forecast Skill in Identifying Extreme Events of Temperature, Wind Speed, and SPI. Then we will have a break to stretch our legs and grab some water or coffee to get ready for the next block. And in this second block, we will have 3 presentations. Christian Viel will show their tentatives to improve the statistical correction of seasonal forecasts by using weather regimes. And Philippe Bett will explain the predictability and application of weather patterns and regimes. Finally, I'll try to summarize what we have learned in this project. I won't talk specifically about the results or scientific details of this or that technique. My talk is more intended as a list of lessons learned during the process that should help the community of developers of climate services. So as not to exhaust the audience patience, today we have limited to only 5 presentations, but the work done under Work Package 2 has been much larger. And so if you are really interested in what you will hear immediately, I suggest you to check the presentations of the SECLI firm Summer School, which took place in the last few weeks. In some of the sessions, you will find topics not covered in this final conference, and in particular, a talk in session 3, very related with the Work Package 2 work regarding the building of multimodal combinations. So I'll stop here and leave the floor to our speakers of the first block. So I'm now happy to introduce you to Volmer Krieken, postdoctoral researcher at KNMI, who will talk to us about the added value of statistical seasonal forecasts. He has a background in meteorology and climate, specializing in seasonal forecasting, climate attribution, and web applications. For SECLI firm, he's working on the added value of statistical seasonal forecasts, adding seasonal forecast information to the TEAL tool and the dissemination of a seamless forecasting system for offshore operations. So Volmer, the floor is yours for 50 minutes.
Thank you, Jose. Yeah, I would like to start with the first slide of my presentation. I will be talking about the added value of statistical seasonal forecast. We'll start with describing the statistical models. Then we'll have a look at how good these statistical models are. And after that, we'll have a look if these statistical models stack up against the state-of-the-art dynamical seasonal forecasting models. So first, I would like to touch a bit on the basis of seasonal forecast. So what gives us predictability on seasonal timescales? We can split it up into 3 separate processes. So we have climate change. We have a long-term trend. Luckily for seasonal forecasters, this is a high source of predictability. Basically, you can see in seasonal forecasting, you can see it as a climate change as a source of predictability. But more on the, so that gives us a long-term trend in our statistical forecast. But we also have the shorter time variability, and to some extent this is related to climate indices. For example, the ENSO, the NEO34 index. There are multiple climate indices over regions of the world. You can see in the graph we have the Pacific Decadal Oscillation, we have the ENSO, which a lot of you are familiar with, the Atlantic Multidecadal Oscillation that gives some predictability also over Europe a little bit, and for example the Indian Ocean Dipole. So if you know the state of a climate index, it can give information of, for example, temperature and precipitation in other parts of the world. And that relation we tend to call teleconnections. Locally, we also have, for example, persistence. If it's warm in a certain place, there's a quite high chance that the next month it might also be warm. And that we call persistence. And sometimes also precipitation can be helpful. For example, if it's a very dry spring, there's a somewhat higher likelihood that the summer will be a bit warmer. So we can use all that information to construct a statistical forecast. I will give a short example of such a teleconnection. This is, for example, the NEO34 index for October, November, December. And the map shows the correlation with the temperature in February, March, April. So that's maybe 4 or 5 months ahead. And you can see that if you know the NEO34 index in October, November, December, there are lots of regions in the world that you also have some information on what the temperature will do during the next month. So we can leverage that information in these statistical seasonal forecasting models. So in the next slide, I will discuss a bit how we set up such a statistical model. First, we'll decide on which model to use. And it's always good to start simple, let's keep things simple. So we have one statistical model. It's based on a multiple linear regression. So hereafter, I'll label it as MLR. The advantage of such a model is it's very simple. It works very well with small data sets. And a bit more detailed step here is that you can easily create an ensemble by looking at the residuals of the multiple linear regression. So if your forecast is very good, then residuals are very small, and you can base your ensemble spread, basically the residuals. But that's a bit of a detailed step. But besides a simple model, it's also nice to have a look at because there are lots of machine learning methods popping up. And one of them is which is used quite a lot, is random forest regression. So without going into too much detail how we've set it up, but generally it's more complicated. The multiple linear regression can only handle linear relationships, but the random forest regression also can handle nonlinear relationships. And you have lots of those in our climate system. But the downside of that it can handle these more intricate relations is it needs a larger training set. It needs more data to train these models. Advantage as well is it does not assume any statistical distribution, and we can extract an ensemble. We can extract probabilities from the model itself. And in a bit more details, we're looking at the trees of the forest to get the ensemble spread. So in the next slide, I'll discuss how we, on the data we base the statistical model on. So we have observational gridded products from 1961 until current. So we have approximately 60 years of data to train our model on. So we're taking, I believe these are from NOAA. So we take the GHCN COMS product. This is temperature observations over land. And for the observations for SST, we'll use the ERSST version 5 product. And we combine this to a global coverage of observations of SST or near surface temperature. We also want to, so we will try to predict temperature, and we'll try to predict precipitation. And for that, we'll use the GPCC, Global Precipitation Climatology Center. Also data from 1961 until current. All the climate indices previously discussed, those are based on ERSST version 5. So these are based on SST patterns. So how do we set up this model? So independent of the multiple linear regression or the random forest, we fit a model for each grid point separately, or grid cell actually. So this grid cell is approximately a degree, or exactly a degree, and which is approximately 100 by 100 kilometers. So we have 360 by actually 140. We're sticking to minus 60 and plus 60 latitude. So we have 360 times 140 models, basically. So we want to know how good these statistical models are. So we create hindcast. So we reforecast the past, basically. And for that, we use a leave one out cross validation. And as said previously, the model is fitted on data from 1961 to 2021. So 60 years of data. In the next slide, I'll discuss a bit how we set up the predictors data. So we have these multiple, we have predictors, we have this, the Nino index, the PDO, and all these, the different climate indices, persistence we're using. And we're basically trying to squeeze as much predictive power out of these predictors as possible. So we're taking from Nino 3-4 index, we're looking at the last month. You can see in the RFR setup, we're taking it from the last month, the lag at -3 months, lag at -5, last 3 months mean, last 5 months mean, last 3 month trend. And we're putting them all in the model to forecast the next 3 months average. For the multiple linear regression that is left below, we're a bit more, we're not throwing everything at it. We're just taking the last 3 month mean and the last 3 months trend. Otherwise it will tends to overfit. Just on so we have the relative simple multiple linear regression model, but for the random forest, we're having a monthly version. So we fit the model for each month of the year. So if we want to forecast January, February, March, we're looking at the past 3 months and over the last 60 years. So then your sample is basically 60, but that's quite a small sample. So we also have another version of the model. It is random forest regression yearly. And there we just throw all months together to have a sample of 12 times 60, which is a much larger sample, but there are some downsides to it. So teleconnections can differ strongly throughout the year. So in that sense, the RFR random forest regression monthly would be better because you don't lose these individual monthly relations. But on the other side, the larger sample size should help for the model to fit better towards the observations. So there's a trade-off, and that's why we use both models. Okay, and the next slide we'll have a look at some results. So the scale metric, we'll use I won't go in detail, but it measures both how accurate the forecast is, but also if the ensemble width is also good. So basically the red regions say the multiple linear regression model is better than the forecast, and the blue say it's worse than the forecast, than the climatological forecast. So we use climatological forecast as reference. And you can see that the upper one is temperature, the lower one is precipitation, the left one is the winter forecast, and the right one are the summer forecasts. You see that especially for temperature, there are quite some regions that show skillful forecasts. For precipitation, there's a little bit less. So if we look at the random forest regression, so the more advanced model, the red indicates the more advanced model is better than the simple model. And you can see that it's the advanced models, the machine learning models that have difficulty improving outperforming the relative simple model. And if you go to the next one, so this was the monthly version of the random forest. We also have a yearly version. And again, it's quite difficult to beat the relative simple model. So the relative simple model shows reasonable skill, but there's not a single model that performs best everywhere. Multiple linear regression most likely performs quite well because it's good with these small data sets. And we believe that for these advanced models, the data set is just a little bit too small to leverage all the advantages that such an advanced model should give us. If you could go to the next slide, because although it shows quite some nice results, we were expecting the random forest to be a bit better, but it's not. But how do these statistical models stack up against dynamical models? And here I'm a bit over time, so I would like to quickly go through it. You see on the left a lot of models. So we use a lot of dynamical models to compare the statistical models against. So we've just selected 11 in total. And on the right, if you could go to the next slide, then I'll go on the right, you can see a figure showing multiple observational products over South America, in this case in Brazil. And they all disagree quite a lot. There can be a deviation of 2 to 3 degrees. And all these dynamical models are based on one of these observational products. So of these dynamical models are initialized from one of these observational products. So we need to use the basically observational average as the baseline truth on which we select how good the models are later. Because if we use the era 5 observations, for example, then the models initialized with era 5 will perform better. So there's always a bias towards their own observed truth, basically. So from hereafter, we'll use the observational average as the baseline truth. So this is the best model. So we're looking at each grid point and saying, okay, we'll select which model performs best. And it's based on the lowest continuous rank probability score. Basically, it's a skill measure. The lower, the better. And you can see if it's yellow, it means one of the dynamical models perform best. And you can see a lot of yellow. So basically, in a lot of regions, one of the dynamical models outperforms the random forest models. So this is from this you can conclude, so what's the added value of statistical models? Well, not that much. But if you could go to the next slide. So what we did, we created a bunch of multi-model ensembles. We computed, so we have 14 different models, and we calculated each possible combination of a multi-model and with 5 multi-model combinations. So we have, with 14 models, we can make 2002 separate combinations, and we constructed each of them and then selected, okay, which model is the best? And for a given grid point, we look at which model performed best. You have 5 models in this best model, because we're looking at the multi-model average. And then we count how many times a statistical model is present. So just from so you can see this basically answers questions. Does a statistical model add value in a multi-model ensemble? And you can see the everywhere where it's more than one, the statistical models add value, basically. And you can see that for temperature, it's a bit more than for precipitation, and for summer, it's a bit more than for winter. And this is to quantify how much more these statistical models improve the forecast. So this is based on the root mean square error. And you can see that in some regions, it improves the forecast, so reduces the forecast error by up to 30 or 40%, which is quite a lot, much more than we expected, actually. If you could go to the next slide for the conclusions. So to conclude, statistical seasonal forecasts are often outperformed by dynamical seasonal forecast in a single model framework. So that was the mostly yellow figure. But in a multi-model ensemble, statistical seasonal forecasts provide a significant reduction in forecast error. The improvements are a bit more profound for temperature than precipitation. I won't go into too much detail because I think Jose will talk a bit more about the independence, but I'll just like to say the added value is most likely due to the independence of the model relative to the dynamical models. So what should we do different basically? And because a lot of forecasts are based on multimodal ensembles, is we should include statistical models in multimodal ensembles. And they should be good, if possible, they should be constructed for each region specifically. Because there's not one single model combination that performs best everywhere. And on that note, I would like to end. Some discussion points if needed, but first, if possible, if there are some questions, I could answer them.
Thank you, Volmer. We have one question from Arlindo Meke. It's what are your thoughts about canonical correlations?
Good question. No, I haven't looked at them, so I have no experience on canonical correlations.
Okay, sounds good. We don't have more questions for Volmer, so remember that you can still put questions on the chat, and he can answer later by writing. As we are a little bit over time, we will move forward with the next speaker. Thank you so much, Volmer, for your dissertation on multimodals. Our next speaker is joining us directly from Italy. Marcello is a researcher and climatologist at Enea. He has been working on the implementation of climate services for 10 years, and since 2012, he has been back at Enea, where he is responsible for several climate services projects, including SECLI. So please help me welcome Marcello Petita.
Good morning, good afternoon, ladies and gentlemen. As was said, my name is Marcello Petita, and I would like to introduce my presentation. So after we saw from the previous presentation how the models could forecast the mean values, we would like to focus more on extreme events. So the title of my presentation try to focus on the forecast scale and identify extreme events in 3 specific variables, so temperature, wind speed, and SPI. You can imagine that seasonal forecast is already something quite complex, and the ability of forecast in 2, 3, up to 6 months, it's could be different depending by the variable, even in normal case. When you try to focus on extreme events, things are even more complicated. You try to forecast something that will happen in 3, 4 months, that it's also extreme, so not near the average or the mean value. For doing that, we decided to take a specific approach. At first, instead of focusing on single extreme events or monthly extreme events, we decided to understand if an entire season, that could be the spring season, the summer season, the winter season, is considered extreme, and how seasonal forecasts are able to predict the extremeness of this specific season. We decided to approach this specific problem because there are some important things that has to be considered when we deal with climate services for energy. For example, when you need to estimate the power needs and you know the next summer will be extremely hot or the next winter will be particularly colder than normal, this is an information that you would like to know. And so approaching the idea of studying the entire season rather than the single month, it's something that could be extremely valuable. Another example could be the hydropower production. So knowing the amount of snow, of course, and how will be the spring and the summer in terms of the amount of heat that will arrive and will melt the snow, it's a very important. And so approaching the study of extreme events in terms of season rather than single month could be a general idea on what is the energy that you could expect. So having an extreme season means that most of the single month can be considered extremes and can have a strong input. So for doing that, we focus on three main variables: the temperature, the wind speed near the surface, and then the SPI. The SPI is an indicator that take into account the precipitation, and I will give you later a better explanation. We would like also to understand how the different models perform in predicting the streams, and so we consider three of the main European models, that is the SNWF, the Meteo France, and the DWD. And this, in this slide, you could already see what are the main characteristic of this model. So continuing now with our next graphic, we could see some important results. But before going into the results, I would like to help you to read with me this plot. So for the next 4 or 5 slides, we will see on the left part the lower 10 percentile, which means that is the ability of the seasonal forecast of predicting the extreme events of the lower part. So if we speak about temperature, the coldest part. On the right part, on the contrary, we will have the 90 percentile, which means the highest temperature. Regarding the line, in the first line, we are going to show the SNWF model results, and the second line is for DWD. We are not showing here the Meteo France data only because we don't have enough space, but we will summarize the results. Regarding the colors of the plot, you have to consider that every time you are looking on something that is red, this means that the seasonal forecast performs better than the climatology. And when you have white instead, you are like the climatology, and all the other colors explain a different ability to predict, to be better than the climatology. Is the Breyer-Skill score. There is another information that we included in our plots that are the black dots that you can see. So the black dots are the location in which the information is not statistically significant. So let's try to have a look at the first plot on the left part. We can immediately see that seasonal forecasts are quite good in identify the extreme season in temperature, especially around the tropical and around the equator. This is quite trivial and quite expected because the climatology and the physical mechanisms that characterize the tropical region are in general stable and well described by the physics of the problem. And so I'm sorry, there is an alarm that switched on nearby my apartment. And if you hear this noise, I can do anything. So, and it's clear that everything related to the tropical and equatorial zone is well predicted, also in terms of extremes. More you go to the poles, the difficulty arises because you have other problems. You have the ferrule cell, you have the baroclinic instability, and also the extreme events are predicted and not so well. I would like to highlight a very important difference between the two models. We can see that, for example, the DWD model, when we look at the lower extremes in the Atlantic region, performs slightly better than the SNWF, and the same for the upper percentiles. So the Atlantic part and nearby the Europe seems that are well described by DWD. And now, when we move to the next picture, we can immediately see how the wind perform. This is the wind speed near the surface, and you can see most of the features are in white or slightly yellow, which means that the Breyer-Skill score is not so high and the performance is not very good. But there are some areas that are still red and describe how the extreme events are well observed in terms of seasonal mean. And immediately you recognize that again, in the tropics and nearby the equator, especially in upper winds in the trade winds area are well detected. And also in the Pacific region between Japan and United States, there is a very good capacity of identify extreme wind during both in SNWF and DWD in the winter time. In the next slides, we are moving to the boreal summer. And again, we have the information regarding the temperature. When we look at these plots and we compare to what was shown before, we immediately see that the area covered by the reddish part is higher than previous, especially in the northern hemisphere. Again, all the part in the equatorial and tropical zone as a brighter skill score relatively high, but there are interesting parts, especially in the Pacific Ocean, which perform quite better also at mid latitude, but also in the southern part of the Atlantic Ocean and nearby the North American coasts. When we look at the wind results, and we can do that when we move on to the next picture, please. For the wind, again, in summer, we have a similar results. So tropical area, very good, but when we go on the mid-latitude, the performance of seasonal forecasts are not so good. Before going to the conclusion to this first part, I would like to show you some zoom and try to understand what is happening in Europe for the temperature. And these are outlined in the next slide, when we can see what happened in Europe for the temperature in DJF, so in winter and in summer. There are interesting parts. So for the lower temperature, we see that the Central and East Europe perform relatively well in winter. Instead, for the upper parts of a high temperature in winter, we have all the Mediterranean area that perform very, very well. The same could be seen in summer, where the Mediterranean area perform relatively well, both during the for lower and higher temperature. You can imagine the next slides we show the same plot for winter, and we will see that for winter there are results that are not good as the one showing temperature, but was expected. The most interesting part, that the yellow part is located in the Atlantic Ocean, and this is very important, especially when you have to predict strong wind in front of the UK and Ireland and northern France, which has a relatively good performance both in winter and also partially in summer. Now, I would like to move and show you in general also the results related to Meteo France. These are the percentage of points that show positive Brier skill score for the different models, so SNWF, WD, and Meteo France, and also for different seasons. We have winter and summer for the upper and the lower and the lower tails. So we see that in general, the seasonal forecast from the SNWF has an higher number of points that has a positive scale, especially for the lower part, but also for the upper part. And Meteo France also provide very good results. In general, DWD and Meteo France perform quite similar, and with a slightly higher results, better results for the seasonal forecast provided by the European Center. Now, I would like to introduce the next slide, in which all the conclusions are prepared. So, as we see, probabilistic skill forecasts are analyzed, and better results are present in the equatorial and tropical Pacifics. And so it's one of the main drivers, as was also shown by a previous presentation. And there is a general good agreement among the different provisional systems in the geographical distribution. We could say that DWD seems to better predict extremes in low wind and temperature in the Atlantic region, mainly in the winter boreal season. Now, I'm going to introduce the results for the precipitation, and in the next slide, this slide, thank you, we can see what are going to use. It's not the precipitation as it is, but the SPI. The SPI is the standardized precipitation index. It's based on value of cumulated monthly mean, and it's built starting from the precipitation distribution for a specific month, for example, January, and then we fit this distribution with a gamma distribution and we normalize it. This is very important because at the end we can compare the SPI along the entire globe, because all the grid points are standardized. And so when we have positive value of SPI, which means an excessive of precipitation, and negative value are related to drought. So the next 4 slides will show you some results. So I will focus on the first slide and then we can skip the other. When you look at the SPI, immediately you see that the results are more fragmented. There is a higher quantity of orange and green value, and red value. And the red value are again concentrated in the tropical region. So this is quite common and quite repetitive for all the months. There are some differences, mainly in the winter season, both in the north and the summer, in the north and the southern hemisphere, which reflect the barometric instability. But in general, compared to the other results, the SPI seems to be better predicted of all in the globe with a patchy results. So if you can quickly move to the next 3 slides, just keeping them for 2-3 seconds, you see that there are similar structure. Thank you very much. For all the different months. And then in the next slide, I would like to stop a while because there are the results for Europe. So this is the SPI for 2 specific months, January and July, that are beginning of the cold and the hot season. And the precipitation are distributed in an interesting way. So for the lower value of SPI, you see that around the Mediterranean area, they are well predicted during the January. Instead, for July, the best prediction is near the Black Sea and the eastern part of Europe. When we look at the upper part, we can see that the central part of Europe and the eastern part are predicted respectively well in January and July. In the next slide, I summarize the results in a table in which we can see what is the total number of positive Bayer skill score for the different models. And you see that more or less are constant in the different months, and most of the all the three model performs quite similarly. So I'm going to draft the conclusion at the end and with the next slides, and we can see that SPI detects, it's allowed to detect positive and negative extreme events better for precipitation, and higher value of BSS are located around the equator. And SPI, it's a good value for a better estimation of distribution tails and skewness compared to the normal precipitation. And if there is any question, I will be happy to answer now.
Thank you, Marcello. For now, we don't have questions on the chat, so please don't be shy. If you want, you can even open your microphone and make a question directly to Marcello. Okay, I will make one short question here if no one else wants. Marcello, you put focus in the presentation, of course, in Europe, as this was a European project, and we have a special interest on what's going on in Europe. But do you have, can you give us a little bit of some details, or if there are some regions where these results are better?
Yes, there is also a question from Sarah Osima later, than
okay.
I see on a right hand. Yes, of course, we focus on Europe because of the scope of the project, but as I said, when we focus on the equatorial area, including Africa and Eastern Asia and also Southern America, the results are quite interesting in the sense that both lower and upper percentiles of the extreme events are relatively well predicted by seasonal forecast. And this is, of course, interesting when you have to work on understanding what could be the effect of extreme events when you are planning energy production, or also when you have to simply predict what could be the impact of extreme weather in particular region, especially in a region where the effect could be serious.
Thank you, Marcello. So we have a question, as you said, from Sarah. We will open your microphone. You can talk, Sarah. Thank you.
Yes. Hello, Marcelo. Congratulations for a very good work. This is very important for us also in Africa. We normally do this in verification of forecasting. I see you have got some comparisons of the model of the ECMWRF and the Meteo France and the DWD. I'm not sure which formula or equation which used to, to evaluate this performance. I will be happy to know the method that you used to evaluate how well this model performed to this region. Thank you.
Thank you, Sarah, for your question. And you're right, I didn't spend too much time explaining what is the approach we use. We use a barrier skill score that is a metric that is often used when you have to perform the capacity of a specific seasonal forecast to predict the future. And this barrier skill score compare the model results with the observation. So we look at the incast. And when it's positive, which means that your forecast is better than using the normal climatology. When you have negative results, on the contrary, the climatology performs better. And for a specific region that you mentioned, the African part is well represented for the extreme, especially in temperature, mainly by the SMWF model and by the Meteo France model. Commercially, the DWD model has a medium BSS that is usually near zero or with a very slow enhancement compared to climatology.
Amazing, Marcello. Thank you then for sharing all that information with our participants. I'm sure they loved it as much as I did. Remember that if you have more questions, you can write here on the chat, and the speakers will try to answer later. Christian Viel is a climatologist at Meteo France, and he's here to tell us about weather regimes and downscaling. So, Christian, the floor is yours.
So I will give you a talk about our tentative to improve statistical correction of seasonal forecast by using weather regimes. Next, please. So the context of this study is the need to feed applications with seasonal forecast. And when you want to download data from portals of seasonal forecast, you obtain raw seasonal forecast data with a resolution that isn't adapted generally to your applications. For example, here in SECLI Film, for the case study 1, you need data at a quarter degree with a good climatology temperature, for example, or if you want to feed this high resolution at 8 kilometer resolution with hourly data, for example, you need to do this adaptation. So a current yes. So a current practice, current method to do the correction is a quantile mapping method. So to apply this method, you need to compute to calculate the CDF, the cumulative distribution function of your seasonal forecast model. So you need to do that over each grid point of the model and for each lead time. And you need to do the same on your reference data. It could be observations or reanalysis, for example. And the application of the method is very simple. You need to just to find the position of the seasonal forecast value on the distribution of the seasonal forecast. and apply it on the distribution of the area analysis, and you obtain finally your corrected value. Next, please. So this is very simple to implement, but every method has its defects. And one known defect of this method is its dependency to the circulation. So I try to illustrate this on this slide. So to look at that, we have used a clustering of daily circulation over Europe on 4 clusters. This is a very typical way of looking at large-scale circulation of over North Atlantic and Europe. And when you divide it on 4 weather regimes, you can look at the bias of model for each of the weather regimes. So here, for example, if you are interested in the bias of UCM developed model for DGF precipitation for the Atlantic ridge circulation, you can have a look on the left on the bias of the model over Europe. And what you'd see clearly is negative bias on the northern part of the main mountains over Europe, Pyrenees, Cantabria, and the Alps. And this is probably due to the coarse resolution of a UCM model over mountains, and its a problem of correctly representing the blocking that appears when you have this kind of circulation, so northern circulation over Europe. So here you have the bias for the 4 circulation, so for the 4 weather regimes, and you can see that the bias is very different from one regime to another. So on the next slide, we propose a modification of the quantile mapping correction in order to take into account the circulation of each day. So the method is called adamant, and is a reference to a method that was applied on climate scenarios and that was adapted to seasonal forecast. So here the method is very comparable to quantile mapping. The only difference is that you calculate a PDF for each weather regime, both for seasonal forecast and for the reanalysis. And the application is quite the same. So you have to know for seasonal forecast in which regime you are, and then you use a PDF of these weather regimes for seasonal forecast and reanalysis. Now on the next slide, we look at the performance of this adaptation of quantile mapping in a perfect forecast mode. I mean, here we have simulated the application of the correction if we knew exactly in which regime we are. Of course, this is not the real case, because in seasonal forecast, of course, we have a forecast of this weather regime. And what we see, if we focus especially on mountainous areas, is that we can have an added value of using this refinement of the quantile mapping method. So we have calculated this for wind speed. So here the graph represents the added value for wind speed, but we have also added value for precipitation over mountainous areas, but no real improvement for temperature. The next slide, please. So then we have used the method and we have applied it to seasonal forecast, but unfortunately, we we don't have the added value in the real case use of this method. I mean that if we compare the method and the method without weather regime, we don't see really the difference in terms of skill. So this is very bad news for us, of course. And the reason why we don't have this, we lose this advantage of using weather regimes, is a poor forecast skill of weather regimes of the seasonal forecast models. So on the right, you can see the performance of 4 C3S models in terms of forecasting weather regime frequencies. So you can see in terms of intervernal correlation for the winter that we have skill. The skill is not 0, but it is too low to be beneficial for the use of weather regime in the quantile mapping correction. So at this stage, we can say maybe that the game is over, but we wanted to go a little bit further and to see if there are some possibilities to have a little added value with the method. So on the next slide, I present just some tentatives to select members among our ensembles in order to see if by a selection of the best members in terms of weather regime frequency forecast, we are able to get back the added value given by the introduction of weather regime. And by doing this selection, so for each year we select the n best members among our ensemble of 120 members, and we look by varying the n value if there is an optimum in the selection of the members, and we found an optimum of about 3/4 of the ensemble, and by using this subsampling of the ensemble, there is a possibility to get back the added value of using weather regimes. So the next and the last slide. So as a conclusion, we see that the direct application of Adamon, I mean the use of weather regimes directly to refine the quantile mapping of skill. So this is quite disappointing, but there are some operational perspectives anyway. If we are able to do this selection of members, so we have imagined two ways to do this selection. The first one is to use an external forecast of weather regimes to select the members. So this is possible by using, for example, statistical model based on climate drivers that can sometimes outperform current dynamical models. And by this way, we could be able to extract and to select some members and to regain in a way the added value of introducing weather regime in the quantile mapping. The second way is to identify windows of opportunity in the forecast. So by using the adapted quantile mapping method only when we identify good predictability in large scale circulation. So the idea here is to look at the context of predictability, and if the context is good, we could expect that seasonal forecast models are able to correctly forecast weather regime frequencies. And in these situations, and only in these situations, there is an interest in using the quantile mapping correction with the refinement of weather regimes. And this is a work we plan to do in a coming C3S project. Thank you. I would be happy to answer.
Thank you, Christian. We have time for some questions. As I don't see any question on the chat. If somebody wants to make a question, just raise your hand. We will open the microphone for you. Sarah?
Yes, thank you very much. Christian, thank you for a very good presentation. Yeah. May I know what is adamant? I failed to understand what is adamant, and may you please give a little bit detail of it. Thank you very much.
Yes, so Adamant is basically, initially it was a method. It was a tool developed to correct to correct climate scenarios, and to do this correction based on quantile mapping, but a quantile mapping conditioned by weather regimes. So this was the first part of Adamant, and this is the part we have adapted to seasonal forecast in order to try to improve the quantile mapping correction. But Adamant is has a wider spectrum, and it can also do a disaggregation of forecast, especially if you want to use a forecast at a time scale resolution that is finer than the original data. So initially it was computed to provide hourly data to feed a snow model. Yes, but here we have just used the first part of Adamant, so this adaptation of quantile mapping using the weather regimes.
We have a question from Alberto Troccoli. Christian, can you explain how do you evaluate the skill for the perfect approach? And did you quantify this improvement, for example, as a percentage or by any other mean?
Yes, so the evaluation of the skill of the perfect forecast is made by looking at the correction. So we have used the same correction with the introduction of weather regimes and without the introduction of weather regime. So we have used error 5 data, not seasonal forecast data. So for this error 5 data, we know exactly, of course, because it is a reanalysis. For each day, we know exactly in which weather regime we are. So we were able to use the good PDF, of course, of error 5 data. So we use error 5 at a coarse resolution at 2 degrees, and we have used the method to produce downscaling at quarter resolution degrees. And so we could calculate a score by comparing this correction of error 5 2 degrees to the real error 5 at a quarter resolution. And the quantification of the improvement is basically looking at the grid points where there is an added value of using the method. And so we just calculate a difference in terms of skill, and with the good statistical test, I don't remember the name of the statistical test, we could see if the difference is significant or not. And so on the graphs that I showed, we have pointed in different colors the grid points where there is a significant improvement. So in green, this was the points where we had a significant improvement.
Thank you so much for that captivating presentation and the answer for the questions to the questions, Christian. It was very eye-opening. Again, insist to the audience that any question you may have, please write it in the chat, even for the speakers that have already finished. And now, to help us get an even deeper understanding of this topic, I would like to ask Philip Bett to grab the mic straight from the UK, where he works as a senior scientist studying the impacts of climate variability at Met Office. Dr. Philip Bett is a senior climate scientist in the monthly to decadal variability and prediction area of the Met Office Hadley Center. His research focuses on developing new ways of using seasonal forecasts. Philippe, the floor is yours.
Thank you very much, Jose. So what I'll be talking about follows on really nicely from what Christian was just talking about. So if you move to the next slide, So we're talking about predictability and application of weather patterns and regimes. So I had an overview of this whole task, which involved a range of people independently looking at different ways of weather patterns and regimes. And Christian and his colleagues at Meteo France did a large chunk of that. But there was also work going on at UL and a couple of parts of work at the Met Office as well. I'm mostly going to focus on the work I did, and Christian has talked about his as well. I can maybe talk a little bit about the other sections as well. Well, let's have a look at it in some more detail. So if you go to the next slide. So all the information here is, I think I already mentioned in the chat. It's in a publicly available deliverable report, which describes these 4 independent approaches to using weather regimes. But I think it's worth thinking about why we might be interested in weather regimes in the first place, because we've all tried to use this technique in different ways. It's because often with seasonal forecasts, you get more skill in the large scale circulation features than in the direct grid cell model output of things like precipitation or temperature. So the idea is that if we use the skill we've got in these large scale circulation features and add some kind of effectively a kind of statistical modeling, as we talked about earlier, linking the weather patterns we can predict maybe down to the quantities we want on a local scale, this might be a really good approach. It might also get us a way of predicting within season variability. Seasonal forecasts are often focused on only being able to forecast a seasonal mean, which is nice, but it's often not what people want. We often really want the variability within the season as well. And often when we're thinking about statistical models, we might only end up forecasting one variable at once, and it's using weather patterns is a very natural approach to produce consistent multivariable forecasts. Maybe you want temperature and wind speed at the same time. So this is a consistent hybrid approach that uses a dynamical model and then some effectively a kind of statistical approach on top of that, utilizing the things that we think maybe we can predict to forecast the quantities of interest for users. So that's why we're really keen on wanting to use this weather regimes approach, why we put so much effort into it. So if you go to the next slide, there'll be a sort of summary of these 4 different pieces of work. There's maybe a lot of words on there, and we don't need to look into it in detail now, but it just sort of advertises that this is stuff that's in the report if you want to look at it. So I'll be talking about my stuff at the top in a minute. I'll just mention that, yeah, thanks. The other sections, we mentioned canonical correlation analysis comes into the question, one of the questions earlier, so it's the section that uses that. Christian's talked about his work at Meteo France and the Adamant method, and Victor at UL also looked into using weather types for wind forecasting in Spain and Italy. So I just want to remind everyone that there's this very diverse set of approaches. So yes, if we go to the next slide, I'll just summarize what our conclusions were. So as a spoiler, I guess we're looking at the standard Met Office weather types for UK winter forecasting. We're looking at how we can apply these for the national grid case study for the UK. But we found that only the weather types that represented the NAO pattern, the North Atlantic Oscillation, could be forecast skillfully. And that meant that the weather type based regression only gave us significant skill for forecasting mean wind speed, and it didn't really help with temperature, and it didn't get that within season variability that we were really looking for. So we didn't find there was any benefit over just using the NAO. So that's the conclusions. Now I'll go through the what we looked at in more detail now. So if you go to the next slide and we start looking at the weather patterns themselves. So there's a set of 30 weather types that are already used operationally at the Met Office in the UK for medium range weather forecasts, and they're very successful. That set of 30 get reduced to a set of 8 slightly simplified types for sub-seasonal timescales, sub-seasonal forecasts. That's out to about 50 days. Again, this works very successfully, and including some of the other work in SECLI firm used these. And there's a product that we have called Decider. There's a link to the paper about these weather types and a web page about the Decider product in the bottom left there. But there's been limited testing on the seasonal timescales. So that's thinking out to sort of 120 days, I suppose, that sort of timescale. So that's what I wanted to look at here. So you can see these 8 weather patterns here. This is pressure patterns. You can see this is sort of based around the UK, looking out into the North Atlantic and Europe. And these are based on the daily pressure patterns every day of the year. They're not just focused on the winter, but I'm going to be focusing on using them in the winter. So 70% of days are covered by those top 4 weather types. I don't know if you go to the next step, maybe that'll be highlighted. Yeah, and the next one as well. That'll be great. Perfect. So seeing those top 4 weather types cover 70% of days in the year, and those top 2 actually cover 40% of days. Those first 2 weather types, they look quite a lot like the NAO negative and NAO positive patterns. So we've given them those labels. So you might think that if we can forecast just the first few out of these weather types, then we've gone a long way to being able to forecast what we need. So for National Grid's purposes, we were really focusing on UK winter temperature and wind. So the idea was that our plan was we wanted to first characterize what happens to the daily distributions of temperature and wind under each of those different weather types. And then, so that's all in observations. And then we start using forecasts of the weather type frequency each winter to construct composite forecast distributions of wind and temperature based on those observed distribution changes. So I'll show that just in the next slide. I'll talk about it more in the next slide. Yeah. So the idea is each winter, you can think of a winter being a series of 90 or so days. Each winter is then composed of a sequence of weather types, and each weather type implies a shift in the mean and the standard deviation of the daily distributions of temperature and wind speed and so on. So you can imagine a winter or a forecast of a winter giving you a set of weather types. So you might say we have 33 weather type 1, 28 weather type 2, 12 weather type 3, and so on, which should add up to about 90 days. Each of those gives corresponds to a change in the mean and a change in the standard deviation, and we can pool those changes in the mean and standard deviation together and get a composite mean and standard deviation from that forecast pool of weather types for a particular season. So the idea is we might start off with just the climatological distribution of daily temperatures, that there are different likelihoods of different temperatures in a winter, and we're going to adjust that so it matches the temperatures we'd expect from the set of weather patterns that we're forecasting for a winter. And the idea was we could, since National Grid was using climatology, we could provide them with this sort of adjusted climatology according to the forecast based on the sequence of weather patterns in a given winter. So we go on to the next slide, we'll have a look at how those distributions do change. So you can see on the left, these strips of histograms. The left column is temperature. And so there's a different panel for each weather type. So the grey histogram underneath all of them is the same in every panel. That's the distribution of temperatures for days in all winters. And then the blue histograms show the particular distribution of days you get under each separate weather type. So we said weather type 1 was NAO negative, and that's corresponding to a shift to lower temperatures that you can see there. And weather type 2 corresponded to NAO positive conditions, and that's shifted to warmer temperatures. You can see similar things on the other weather types. And the right-hand column of those histograms then shows the same thing for wind speed. So again, you can see lower winds for weather type 1 and higher winds for weather type 2. Characterizing all of those changes in terms of the detailed histogram is a bit complicated, so that's why we're just using the mean and the standard deviation. So you can see those in the scatter plots, like the top one for temperature. You can see that weather type 1 again corresponds to a reduction in the mean and a somewhat of a reduction in the standard deviation, whereas weather type 2 has got a much narrower and enhanced distributions. You've got an increase in the mean and a bigger reduction in the standard deviation, and so on. So this is good. This means that the weather types do indeed lead to different distributions of temperature and wind speed. So we could just use observations to give us sort of perfect forecasts of weather types. So where we know the sequence of weather types in every winter. So we can then test this method of coming up with a composite mean and standard deviation of daily data each season, and see what that gives us for our seasonal mean temperature and seasonal mean seasonal standard deviation of daily temperatures and wind speeds. So we're testing the method that we want to use with National Grid, but we're doing it with full knowledge of exactly what the weather types were in each season. And this seems to work pretty well. So we've got significant skill for mean wind speed and standard deviation of wind speed on the right there. Got the correlations written as the numbers in those panels, and we can do seasonal mean temperature as well. That's great. Seasonal standard deviation of daily temperatures, so the within season temperature variability, not so good. It's a little bit borderline, and clearly the variability is too low as well. But still, this is a promising start. So on the next slide, I think we go to look at what happens when we actually use a seasonal forecast model instead of the perfect knowledge of the weather types. So these panels on the left, the key thing to look at is the black line, which is the true frequency of each weather type in winters, and the red line, which is the forecast, the hindcast models, frequency of weather types each winter. So these panels are showing how good the model is at getting the number of days in each weather type correct in each winter. I'm sorry that the text on these is a bit small, but the gist of it is that only the top two weather types, weather type 1 and 2, the NAO-like patterns, are the only ones where we could get significant skill. So we get, broadly, we get the fraction of days per winter in weather type 1 and in weather type 2. We can do that significantly better than climatology, but the other weather types, not at all. This doesn't mean the whole thing's a waste of time. However, our method doesn't just use the frequency of days of each weather type separately. We're pooling them together, as we discussed earlier. Yeah, so we can see now that we've now apparently lost skill in forecasting the temperature and in the wind variability. We can still forecast the seasonal mean wind speed perfectly reasonably. That correlation skill of 0.51 in the top right there, I would be very happy having that level of skill from seasonal forecast system for UK winters, so that's fine. However, it's no better than if we just used a seasonal forecast of the NAO to predict wind speeds. And just using a seasonal mean NAO is far simpler than this complicated method using weather types and composite changes in the distribution of daily wind speeds and so on. So we haven't made the forecast worse, but we have put a lot of effort into not improving it, in a sense. So if you go to the next slide, an important question is you can think of many things like, did we try this or this to improve it? We tried a lot of things to try and improve the forecasts, different ways of assigning the weather types, we tried using fewer weather types, that didn't help at all. We tried different ways of using the ensemble, so we were slightly surprised that so our seasonal forecast system is an ensemble system. We produce a large number of forecast runs each time, and we found that using daily ensemble means from the forecast system actually improved things, which was slightly surprising. And we found that if we shifted the lead times to a little bit later on, that had a small improvement as well. But the plots I've already shown are the improved ones, so that's as good as we managed to get. So if we jump to the next slide. So the conclusions that we got from our work, and I think these are consistent with the results across this piece of work, across the different approaches, was that the classic or standard weather regimes, so the ones we've shown based on k-means clustering, but also other work based on EOF analysis, for example, standard approaches, they can appear really promising in some contexts under perfect forecast conditions. But then when we actually try and use the seasonal forecast model, the climate model, to predict the weather regimes, we find that they're basically not good enough. The seasonal forecasts of weather regime frequencies are usually not significantly skillful, and that really limits their use in real forecast conditions. I don't think this is the end of the world, however. I think what we've shown is that just using standard off-the-shelf, if you like, approaches to weather regimes isn't very good, but there can be maybe other approaches, other approaches based on similar ideas, but very much tailored. I still think that might offer some improvements in specific cases. And this goes back to, I guess, what we've been saying all day, in that a very focused, tailored approach is likely to be better than using something that exists already, using some standard approaches, for example. So through this bit of work in SECLI firm, we've tested different approaches to using weather regimes, and we've done this independently. So the work I was doing has got a lot of similarities with what Christian was doing, but we use different models and we have different user requirements in mind, and it was all done very independently, even though we've come to very similar conclusions. And that goes for the other parts of work as well. Developing with user requirements is really important, as Claire was discussing earlier, and that, I think, maybe holds the key to improving things along these lines. I think that's all I have to say on the, I don't think there's another slide. Yes, questions. So I can talk about some of the other things in more detail if we like, but I think we're coming up to the right time now, so happy to take any questions.
Thank you, Philippe. We are over time, so if we don't see any question on the chat, if the audience wants to make any, please use the chat, and Philippe will answer, unless there is a very quick one. If not, thank you so much, Philippe, for sharing your time with all of us. It has been a pleasure listening to you. And now, last but not least, I guess you will be familiar with the next speaker. For closing this session, I will summarize some of the lessons learned by the partners while working on the tasks of the Work Package 2. I'll do so through examples extracted from some specific studies where these outcomes are more apparent. Historical observational data is key to train the statistical models and to validate the seasonal forecasts. Advanced post-processing methods generally require more data and statistics than historical records can provide. And that's why it's a general practice, as we have done in the SECLI Film project, to use reanalysis data as our best approximation to the real-world observations. In all the presented works, we have used ERA5, the most recent reanalysis data set from the European Center for Medium-Range Weather Forecast. However, to develop operational climate services based on seasonal forecasts with some success, we cannot rely solely in the reanalysis, and the availability of in-situ observations of the variable we want to forecast is key to optimize this kind of local forecast. Slide regarding model selection. Why we need a model selection? Well, in the rows of this table, we can see the variables we used in the project, and in the columns, the different seasonal forecast models, plus, of course, the reanalysis data used for validation. So the questions that one may have are the following. Is there a model which is better than the others? Is there a combination of models which is better than any other model alone? How I or we should select the best model combination? The answer to the above questions is universal, or depends on the place, variable, or other factors. And as you may imagine from what we have heard until now, the answer is that it depends. So the optimal selection of models is different depending on the region studied and the particular phenomena we are interested in. Each model has its own distinction and provides added value for some region, season, or variable. And by using independence information, it is possible to reduce the number of models and data to produce the optimized forecast. If we move to the next slide, okay, thank you. We can see this graphically. in the following plot. Here we can see that each model has a particular skill for a given variable, area, and time of the year. In this case, the model for this particular case we are studying, the model from the German Meteorological Service is the best one, followed by the European Center, the Met Office, and so on. But what happens if we combine the models? When we have a combination of two models, we see that automatically the skill scores increase in average, as well as the minimum and maximum values. So we are like switching everything up. And what happens if we increase even more the number of models? As we add more members, it might happen that the combination with higher skill still improves until we reach a maximum, which in this case is achieved, as you see, for 5 members. After this maximum, adding more models to the combination reduces the value of the maximum achievable skill. As we see now on the right of the plot, with an exaggerated vertical scale, we can always find a combination of any number of models which is better than the best individual model. And we can also see that the optimum number of models can be smaller than the total number of models available. And how are the optimum combinations, how we can find them? It has been found in the project that the combinations are better as the models used are more different. So in this plot on the right, is shown the Braille score covariance for each pair of models. And this score is a measure that we found in the project of the independency of the models. So for the purpose of increasing the skill of the forecast through combination of models, we should consider not only their individual skill, which is also important, of course, but also to have lower covariance between them, as the ones here in this example, the ones in red. The ones with lower scores are the ones with more independency between them, so the optimum participants in the optimum combination. We see that not only that, we have looked for the optimal combination of models, the one that gives a higher skill for different areas of Europe, and also for Colombia, because there was a special focus in the project for that part of America, for different times of the year and for different variables. And as can be seen in this table, for each case, the result obtained is different. The number of models with which the optimal combination is obtained for each variable, time of year, and region is different. Also, the skill values for the individual model, best combination, and all models have totally different values for each case. So what is clear is what was explained in the previous slide. In the majority of the cases, the best combination provides a statistically significant better skill score than the full multimodal combination. At the end of the day, the end user doesn't care about the forecast skill according to the conventional indexes used by the scientific community, because they are not interested in how the standard variables as temperature or precipitation behave at grid points in a low resolution model, which in the end is what a seasonal forecast model is. What the end user wants to know is the forecast of the variable of their interest, which can be a derived variable. So something that cannot be extracted directly from the model, exactly at their location. So also a downscaling process is required to obtain the value at that point. The added value of the forecast with respect to, for example, climatology should be shown for the specific application. To link the raw model output to the target application, we need a tailored statistical processing, because there is no universal solution. Let me illustrate this with some examples of tailored applications, some more successful than others. In the first example, we want to help Shell in their offshore operations in the North Sea. Currently, they consider June, July, August to be sufficiently calm for maintenance of their assets in this area. The question is, can we forecast when the probability of calm conditions in May will be similar to the climatological rate for June, so letting them to extend the operational window to May? The method consists of performing a principal component analysis, and we are recovering here the question from the first talk. A principal component analysis on the wind field and wave field, significant wave height, SWH in these plots, okay? Then perform a canonical correlation analysis, CCA, to relate the two PCAs. Finally, we make use of the seasonal forecast of wind to assign the corresponding principal components. Through the canonical variates, we can make then a forecast of the significant wave height. And the question would be why we are making things in such a complicated way and how this forecast performs. Well, we can see in the two maps on the left side, please previous one, yeah, thank you. We can see in the two maps on the left side how the correlation of the principal components is significantly better than the direct correlation between wind and wave height. And this leads to some skill in the wave forecast that was not in the previous scheme. So, however, this skill is basically driven by forecasted outlier events. So this kind of forecasts still require more probability distributions than single values. As we have seen, and this you will hear now something more or less that was already introduced by Philippe. As we have seen in the previous presentations from Christian and Philippe, the classic daily weather types aren't very useful for seasonal forecasts, or at least not as useful as we would like. Although the weather type may be skillful in predicting other variables as temperature or wind, it doesn't work in this context due to a lack of skill of the seasonal forecast models in predicting the weather patterns itself. However, tailored regime-based methods can still be useful and provide improved forecasts in specific cases, as shown before. For example, the downscaling was quite successful for national grid, where the focus was more on plausible scenarios than predicting at high resolution. Another example is the forecast of wind and precipitation in mountainous areas when the predictability of the weather types is or can be slightly better. Here, we have applied a technique which was successfully applied already in decadal forecasts of the NAO, so it was worth to testing its ability in seasonal forecasting. In part, the signal is small because the model tends to smooth the results, and then the forecast variability is smaller than the actual one. This is a limitation of the model itself. So to overcome this limitation, we plotted the observation of the NAO, here represented by the black line, the ensemble forecast, the cyan dots, and the ensemble mean, which is the blue line here. Then we inflate the signal of the ensemble mean multiplying by the ratio of variability observed over the variability predicted, obtaining what we see here as the red line with amplified anomalies in the next plot. Thank you. Then we created a new ensemble by selecting the members which are closer to the inflated anomaly forecast. However, there is only little improvement of skill when compared with direct forecasts of temperature and precipitation in some areas. In others, the root mean square error can be even higher over direct forecasts. So what is the lesson here? A technique which worked pretty well for decadal forecasting of NAO has limited application for the seasonal forecasts. And it should serve as a lesson that every solution must be tailored to the specific problem. Also, to keep in mind that more sophisticated techniques doesn't necessarily improve simpler forecasts in an operational setting. Although we have seen the reverse side just 2 slides before with the forecasting of the wave. Okay. So if we move to the next slide, to evaluate the probability of extreme cold winters over the UK, Hindcast ensemble of 2,280 winters was developed. And we see in the plot here the distribution centered in 0 degrees anomaly, and the red lines showing real extreme winters with their measured temperature anomaly. We see there are a few ensemble members at the left and the right of the historical extreme winters represented in red. What does this mean? We see that if we create a composite of the mean sea level pressure of the 5 warmest or coldest members of the simulated ensemble, and we compare them with the real 5 warmest and coldest winters, we find similar weather patterns which indicate these situations. Cold winters are characterized by a negative NAO pattern, which with cold continental air advected over the UK, while the warm winters have typically a high pressure over the Mediterranean, which advects warmer maritime air over the UK from the Atlantic. So, although the studies performed in the project demonstrated that seasonal forecast models capture only around 50% of anomalies over Europe for lead time of 1 month, the Hindcast has proved to be useful to understand the risk of very low probability events. And that was all I expected to explain to you. I don't see questions in the chat. We are very close to the end of the time, but
okay, that's fantastic, Jose. That was a really, really good summary of what's been done in Work Package 2 with the science of seasonal forecast, and great way to summarize all the work and also how it was explained. And of course, we had a great lineup of speakers today, from Claire, and Former, Marcello, Phil, and Christian, all excellent presentations. As we said at the beginning, we couldn't cover all the topics, although Jose managed to touch on most of the things that have been done, but there is actually a little bit more, and you can learn about those additional things, as well as more about what's being presented by reading the reports. Some of them will become available soon. They are being reviewed, some of them. I'm just waiting to see if there is any other question for Jose, maybe others. We've got 1 or 2 minutes before we close. In any case, you could see that the amount of work that has been done in SECLI Firm. Personally, I was amazed by the quantity and quality. As we said, sometimes we didn't achieve the results that we were expected, and therefore they are considered not positive results, but still very useful lessons that we will sum up also in publications, together with the lessons from other part of the project that we'll look at tomorrow. So tomorrow, same time at 12 UTC, we'll have the second day where we present the case studies and in fact a selection of them, because again we cannot cover everything, but we decided to present 3 of those case studies and go into more detail about those case studies rather than covering all of them. And we got a very interesting program for you lined up for tomorrow, as well as Tuesday on the 19th for the final day. So thanks again to the speakers and the audience, of course, today, and all the organization behind the meeting. But we'll come to the thanks on the last day. For now, I'd just like to wrap up the day and invite you to come back tomorrow at 12 UTC. Thank you very much again, and have a good rest of the day.